During the school, we heard about frequency centimeter emission, epoch of reionization. But there are other observations. So I come from CMB background. So from CMB, cosmological radiation, you can also consider the epoch of reionization when it happened. How? So that is what speak about it. But say JWST, it will also tell when the forces are formed. So there are different observation probes. It always helps in understanding the epoch of reionization. And you can use those other probes to learn about non-standard physics also. So that Rishi talked about. So my focus is mostly on about the CMB observation. So in particular, CMB temperature fluctuations, you know, but still, so there are background properties. There are some degeneracies between cosmological parameters that do not tell you about the epoch of reionization, but CMB polarization is the proof. The Planck is a satellite which measures this CMB polarization very accurately. So tell you what it measures and how you can use to consider the epoch of redshift of reionization, or the tau parameter, which is the optical. So just go through the basic thing which you know, but it's useful to revise. So we are in the standard cosmological paradigm where the universe is expanding. It's also accelerating, and it has two major components, which is dark matter and dark energy and cold matter. So that's why we have lambda CDM model. So if it is expanding, it means that when we go back in time, it becomes smaller, denser, and hotter. So the temperature goes inversely proportional to scale factor. When you go to back in time, the temperature becomes higher and higher of the universe. So this is cartoon picture which basically captures the thermal history of the universe. So at low temperature, the photon has low energy. So this is the timeline of the universe. So we are here somewhere 13 billion years, and we are basically looking back in time. So currently the universe temperature is 3 Kelvin. Okay. So we have neutral hydrogen atoms, low energy photons. But if we go back in time, the temperature becomes higher. So the low energy photons become high energy photons. So high energy means by blue is but still lights. So if you go back in time, there is photons and electrons. They have a high cross section. Because of that, the mean free part of the photons are very less. Okay. So all these things like protons, electrons, photons, they become like a fluid. We call this as beyond photon fluid. Okay. So this is something around this temperature. So before the recombination, from 10^3 to 10^5, okay, around that temperature. So as we go back in time, photon has more energy, and this plasma is opaque, so we cannot see those photons because of the cross section of the photons. So we see anything by through photons. So the photons should reach us. So at some point, which when the universe cools down to around 3000 Kelvin or redshift of 1100, this protons and electrons, they recombine and form hydrogen atom. Okay. And these photons, they don't have anything to scatter. So they don't see the free electron, and these photons are coming streaming towards us. So all these photons from redshift of 1100, assuming there is nothing there, so it is just streaming towards Earth, and in Earth there are like ground-based satellite or space-based satellite. It's just capturing those photons. So it is. So in my image, I showed it from one place, but it can happen from multiple places, and this we called as last latent surface. So this photons has a temperature of 3 Kelvin roughly. Okay. But on top of it, there is a tiny fluctuation on top of it. So that fluctuation is order of -5 Kelvin. So these fluctuations are necessary for the structures to form. So there are some regions which are under dense, some regions which are over dense. So that is represented by blue and red. So red means slightly higher temperature compared to the mean temperature, and blue is slightly lower temperature. So we are interested to make an image of this fluctuation. So that CMB experiment is basically trying to get this map, like 21 centimeter signal. So you basically measure the microwave background. So this signal, we observe this in microwave frequencies around, it peaks around 100 gigahertz. Rishi or somebody is that. So that is the it's basically first picture of the universe when the photons are coming towards us. But while it's coming towards us, it sees everything between us and the last second. So basically, this is the cartoon picture of the universe, or current understanding of the universe. So something happened from Big Bang. So popular theory is inflation. So standard model, Big Bang model has some problems which inflation solves, like horizon problem and flatness problem. So there is an exponential increase of the universe, space expanded exponentially, and then the theory was formed around 400,000 years, when the universe was 400,000 years old. And then after that, there is a phase which is dark age. There was no structure was there. Then the first star was formed, and it starts to ionize the medium, and the universe becomes deionized. Okay. So this CMB is called recombination era, and this is deionization era. And all this thing, what we measure, is encoded the information about the background and what is in the reionization era. So we can constrain what is when the first structure was formed or when the universe becomes ionized. So we can get it through CMB. So that is the broader idea. And this CMB also has information about the inflation. So those people who are studying early universe, so there is a inflation models, the different models. We can constrain those inflation models through CMB observation. So, like simple models produces Gaussianity. If you find you can see tell that you can start ruling out those some of the models. So the idea is we want to measure this fluctuation to higher and higher accuracy. So it started with COVID 1992. So it first detected this fluctuation of -5 Kelvin. Then the WMAP came. It measured around 1 degree scale. And with plan it goes to 5. So in temperature, basically, you want to extract as much as information from the image, and this is a cosmic variance limited experiment. So from the temperature, whatever we can extract, it is extracted through time. So even if you launch new generation satellite, you cannot extract more information from the temperature fluctuation. Kobe is 7 degree. WMAP lowest resolution, highest resolution is 15 arc minute. So different frequency, high frequency with different beats. And its highest is 5. So it's 3 times better. So WMAP worked for 9 years. So 9 years of WMAP is equivalent to 1 year of Planck. Were WMAP observed for 9 years. It is at the similar level in terms of the same field, the sensitivity, but the resolution is higher, so we can extract more information from that. There is some cases where red, but the red are also nearby. They are not random. Yes. So this is called CMB anomaly. So just one relation of the study. So the Planck map, for relation, people expect it to be close to the mean, like there should not be patterns or anything. there are many anomalies which are found in the CMB. So there are hidden here. So there is a cold spot here, which is colder than what we expect from a Gaussian distribution. So CMB is expected to be Gaussian distribution, which at 1 degree scale, the fluctuation sigma is like 70 micrometers. So the temperature is much in the negative side, higher than 5 sigma, less than 400. This large scale pattern, you see, this basically leads to hemispherical. So if you divide the space into two parts, so this is a northern hemisphere, this is southern hemisphere. So there is two hemispheres. So assumption is CMB should be statistically isotropic. So even if you have a smaller scale fraction, you can extract the information of the cosmological parameters. But it seems that to extract from two different part of the sky, 50-50, to get different amplitude of the power. It does not change the cosmological parameter, over amplitude is different. Then people try to find what is the logical explanation. So they launched, previously it was found with WMAP. They thought that there are some systematic with WMAP, then the plank was launched. Some of them goes away, and some of the bigger ones still remains. It is going to do, there is low power, what is expected from a standard lambda scale. So then people say, because there is a one sky, how many times we observe, we will see the same thing. We go to some other galaxy and observe the CMB. You don't get a different level. Whatever you do, it's like it's not an instrumental artifact. It's like one sky, so it can have some spatial behavior. Just like a Gaussian distribution can be like 3 sigma away. So maybe you can see something which is not expected. You would expect from the mean of the distribution. Okay. So here is the resolution of the map. So it's basically going higher and higher resolution. People stop working on CMB. It's not true. So there is another mission for light that will launch in 2027. There is a Japanese mission, Japanese and European mission. In temperature, they can extract whatever they can extract. They extract it already. Now the next target is polarization, which is important for 21 centimeter. Polarization, not all the information is extracted. It's roughly like 20 or 30% is just we know. So there are a lot of things we can extract from the polarization. So the light bulb is basically targeting for epoch Reionization, this tau parameter, optical depth. So that is one of the main targets. And also they are trying to measure the parameter gravitational waves or the B mode. Okay. So this CMB has a black body temperature of 2.7 Kelvin. So this was first measured by Kobe. So they have a absolute calibrator. So they can measure the black body temperature. So they know what is the temperature. After Kobe, nobody measures the absolute level. So we always measure the differential. Or we look at two different directions and subtract it, and that is the differential measurement. So the fluctuation people are not interested, not on the. So that is what we need or what we want. In real sky, when we observe, we don't see CMB, we see extra stuff, which is the red ones, which is coming from our own galaxy. So these are photons. So now you know what photons. And many of the techniques which are used in 21 centimeter, they are borrowed from CMB. So CMB community first encountered the photons, and they want to extract a CMB, but it is hard to find it's hard to know what is photon and what is the CMB. Only thing people know that CMB has a black body temperature, so they use this property that in thermal temperature it is constant to extract the CMB out of the photons. But these photons are very complicated. So there are at low frequency, there are synchrotron photons, there are free emission. Okay, so some of them were shown in this talk or in the tutorial. At frequency, there are dust emission. And if you put more and more channels. So the idea is, if you have more channels, we can measure the spectral energy distribution of the foregrounds and can model it out and get to the CMB. But then there are lines, like the carbon monoxide line, which feeds excites at 1150 1.5 gigahertz, and they have line condition, so 120 or 221. So it happens at 150, 220. With client, they found 8 CM line, which feeds at 100 gigahertz. So all the many frequencies are better, but once you have starting having more frequency, other photones also start to come into the picture. So it's not always help that more frequency, more expensive mission, but it's not guaranteed that it solves the problem. Yeah, so that is the next slide. So let's see temperature. This is the frequency around 100 gigahertz. Foregrounds are this is a CMB, the blue. There is a synchrotron emission, free phase. So here only the dominant ones are plotted, not all of them. So there are many foregrounds like cosmic infrared diode and isotropies. There is a zodiacal light from planetary details. So there is a Sunai Zeldovic effect, which she talked about. There are point sources, radio sources, infrared sources. So in this plot, only the big ones are shown. Okay. So around this frequency, like around 90 to 100, basically the CMB dominates over the other foregrounds. So that's why it looks cleaner. So at least from the observation, you know roughly what you like. This blue region is like CMB, so it's same in all the frequencies. So even from that patch, let's say 10 degree by 10 degree patch, you can estimate the power spectrum and calculate the cosmological parameters. And it is you will get huge error bar. So more slides are better, reduce those error bars. This is the more data sample, less error. In cosmology, in CMB, people claim that they measure the cosmological parameters to an accuracy of 1% or better. So the error bar on the parameters is less than 1%. You want to even 1% foreground is there, you need to remove those foregrounds to actually tell what is the cosmological parameters. And the next generation is targeting for 0.1%. So that is the challenge. In polarization, it is much simpler because not all of them are polarized. So we have only synchrotron and dust. So this is in CMB, we have a, if you consider foregrounds as a noise, we are some region we have high signal noise, some region you don't see the pattern. The foregrounds are 2 orders of magnitude higher than the signal. So it's very difficult to clean the galactic. In reionization, it is in map space, it is 3 orders of magnitude higher. Power spectrum is 6 orders of magnitude higher. People are trying to clean the foregrounds, which is 6 orders of magnitude in power spectrum. So CMB, till date, we do not get a good galactic plane map. It is always masked, which is just 2 or 3 orders of magnitude higher. And even if you know that it has a hypersphere, it will be much more challenging problem for 21 signal detection. Here the problem is that there are too many foregrounds, and the foregrounds are a complex behavior. 21 centimeter, assuming the foregrounds are simple, you can clean it. If it is well behaved, some power law properties, or even if there is a polynomial, like second order, third order polynomial, you can fit the foregrounds, then it's good. Otherwise, it's very complicated. So there is a leakage from polarization. So some of the foregrounds, like synchrotron, is polarized. So there will be leakage from polarization to intensity. So it does not matter in intensity is well behaved or not. The polarization leaks also. It is the problem. So synchrotron is polarized up to 75% fluidity. With Planck, we measure it. It is maximum polarization is like 30% because of the line of sight effect. So there are different component operation methods which client basically extract this CMB map from this multi-frequency computations, and some of them are also used by H1 scientific community. So they simulate the maps and they apply these algorithms to extract the data. So some are blind method where you don't assume anything about foregrounds. Okay, so you assume that you want to reduce the variance of the map, so that is the metered ILC and the splitter map. Some algorithm they assume like the Bayesian fitting, they assume the SCD of the or secondary distribution of the foregrounds. So something is good, this is bad. Like method you get an answer, but you don't know is correct or not. If you Bayesian parameter fitting, you can get all the foregrounds, then you can verify if those foregrounds have those behavior which you expect from theory. So that is a validation. Then you get a CMB. In blend method, you just get a CMB and everything is thrown out. Foreground noise. So some of these you can go on into foregrounds also. Good thing is all this method give you roughly the same answer. So these are the full maps. So galactic plane, the residual is not in the residual, and this in the galactic plane, these maps are very different. But broadly, all the different methods give the same answer. So that gives a confidence that whatever cosmological parameter we have, it does not depend on the method. In W1, they use only one method. So then comes to the, so this is up to the temperature part. Then this signal is also polarized. So,
if I understand correctly, you mentioned somewhere that there's no more information that can be extracted. But I heard people talk a lot about trying to measure even the spectral distortion in the black body spectrum. What are they talking
yeah, that is the monopole task. When you have the absolute level, so you have 2.7 plus minus some fluctuation. So from fluctuation, we exert all the information. Now people are trying to measure the absolute temperature. So it is the black body temperature. Now there is, that is the assumption, but maybe there is a distortion. So the distortion or deviation from the black body, where the upper limit of the distortion is less than 10 minus 4. So people wants to measure those distortion, which will give you access to higher redshift, like from 1000 to 10,000.
about? You don't depend on which part of the sun.
Maybe they depend on, but you need to measure first the absolute level, not the fluctuating part. So after Kobe, you don't measure the actual level. The problem is that if you have the actual level is very high, the mean level, 5 times higher. So once you have to subtract those numbers, you introduce a lot of error in the subtraction. So when if you go to the differential measurement, it is much easier. So then those people, they're not interested in the circuit. So in 2.7, what is the, you need to correct for the dipole hour movement around the like CMB frame. After that, it is that is what spectral distortion is. But the foregrounds are also will come here. And the foregrounds is another level of complexity to measure those spectral distortions. Okay, so this CMB is polarized. So it is linearly polarized. So it is linearly polarized, but is generally given by Stokes parameter Q and U. So people try to measure the V parameter circularly of the CMB, and it is very low. So latest measurement is from spider experiment, and they found it is very close to 0. So CMB is not separately polarized; it's linearly polarized. It's defined by this Q and U Stokes parameter. So there is a quadrupolar anisotropy during the last cutting surface. So there are two red spots, and because of the scattering of the electron through Thomson scattering, we see net polarization. So the net polarization of the CMB is around 10%. So this Q and U are measured with respect to local north. Okay. So if it is vertical, it is greater than 0. If it's horizontal, it is less than 0. If it is 45 degree, it is only U parameters. So by looking at the any map, Q and U maps, we can tell what is the net polarization, like if the polarization are aligned in particular direction. So if it is only negative Q, it is like horizontal, positive Q is like vertical. So this polarization is like between two quantities.
The system of the coordinate system, what is the area?
This is the IAU convention. So when you measure polarization, it is anti-clockwise. So you define local north, and with respect to that angle, you measure what is the angle polarization. You can always define your own one, but basically all the astronomy community they follow the IAU convention. So that is how you define the polarization angle. If negative means the polarization direction you want to put, suppose U is 0, Q is negative, so it means that polarization is in this type. So it's like a linear polarizer. If you put, it will allow all the light to pass. If you put the linear polarization at 90 degree, you will have to. This is the convention that is shown here. So it is like this. It is Q, and it is also Q, but in between it is Q. So these are between two quantities. If you rotate the system by angle theta, your QU rotates by into theta. The same thing in 21 centimeter. People are start looking at the polarization of foregrounds. So the signal is not polarized, but the foregrounds are polarized. So that polarization leaks into the foregrounds.
During the Epoch of Reionization, CMB also scattered, and that will introduce another analysis in the
I come to that. Okay, so this QU polarization is very difficult to. Okay, because if you look at each region and see which direction the polarization is. So the convenient one is to look at E and E modes. So E modes, if the in a certain region, if the polarization vector are in this direction, that is this E mode, or if it is rotated, you rotate this by 90 degrees. This is like E mode. So it has a mirror symmetry. The B mode is you just rotate by 45 degrees, it is like a B.
if I see the polarization, each of those lines is one
pixel. One pixel. So right. If you go to one pixel, here it is all horizontal. Then here it is vertical. So you go to one pixel and see locally what is the direction of the polarization. Based on that, you can tell whether it's E mode or B mode.
If I see the polarization is like this, then that is E mode. It's like this, that is B.
This is basically Helmholtz theorem. So any vector you can write as a curl-free component and drag-free component. One of them is E mode and one is B mode. The polarization vector is the like from you measure this, what is the direction of the polarization. The advantage of this is that it is a pseudo-scalar. So you can treat them as like intensity or the temperature. So you can measure this power spectrum, and this power spectrum of E mode is basically what we are interested in. Okay, so this pump is basically coming from the recombination area, or it contains the optical depth. Yeah. So this is the temperature power spectrum, the original map I showed. Once we have Q and U, we can make to E and B map. Is E power spectrum looks like this, and this is the B mode power spectrum. And then you have three options, T, E, E. You can always cross correlate T with E with a CL. So you take ALM, ALM, E. So E is not zero. So there is a T from the CMB. So there is a negative part is shown in positive part as CL in the dash line. This is the BB power spectrum. This is the lensing BB potential. Theoretically, we don't expect any T or E. Both should be zero. Observationally, we measure it. So it can come either from the instrumental systematics or there is some cosmic bifringes which can cause this. So this is very active field of research which people are trying to understand why there is a non-zero TB. So they rule out all the foregrounds and all those things. And, it can be of primordial origin. This is the theoretical. I have a better one from Latin. This I think will. So we have this E-mode power spectrum. To go quickly. B-mode. It has two parts. One is the primordial part and the one is the lens. The primordial B-mode is coming from tensor perturbation. So it basically imports the information about the primordial gravitational. So it's not detected yet. There are upper limits from bicep experiment, and people are trying to detect this signal through space. From Indian community also proposed that this is now measured at like 10 sigma, 40 sigma significance of the climb. And climb, and the matter, whatever is between, is mostly dominated by dark matter. So basically, this is one way to measure the dark matter distribution. So people wants to know how the dark matters are distributed. So from you can actually make those maps. So currently we have that map, which is like signal to noise is order of 1. But in terms of power spectrum, because we are averaging on different source of faults. Okay. So we want to measure this E mode power spectrum. We will tell about the operation. But the complex is that we don't get the directly. We have to go through the foregrounds. So these are the actual data, and the foregrounds are much higher than the. So it's not like CMB temperature where we know that some region the CMB temperature dominates over the foregrounds. In polarization, always the signal is less than the foreground. So we don't see it. We do same concentration method, assuming that it works, and whatever we get it is the CMB polarization. Okay. So just to show you, this is the signal of tau point, and this is the level of foregrounds. 5, 150. So this is from dust and from synchrotron. So the synchrotron is okay, but there is a dust which is higher than the signal we are trying to do. So this peak is only at 4-5 L's, but the problem is that you cannot do it from the ground. You need a space mission because to get L is equal to 2, 3, 4, 5, 6, like only limited number of L's. To find this peak. Okay. Okay. Any question? It's of Cl, so it's L into L plus 1 Cl.
Polarization, polarization.
So you get a so there is a linear relation from QU to ENP. So ultimately you get a E mode map and an E mode map. Once you have a E mode map, you can treat like a temperature and you can just calculate its power spectrum. So that is CLE. E mode map, you can do that. Only thing is to go from QU to EA, you need a full step. QU to EA. So it's not each pixel you have to go. Once there is a relation, direct relation. So you have to make a Polarization tensor Q plus IU and Q minus IU, which can break into spherical, spin to spherical this, and then you combine them to make E and B.
The payload signal is not yet announced.
No, the observed map has a lot of photons. So you measure the B mode, but you don't know that B mode you measure is coming from primordial or photons. So most of them, if you throw away, then you don't measure. Most of them is basically the photons. This is from lambda CDM with tau is equal to 0.6. It is other cosmological parameters, depends on the other cosmological. So you want to measure tau. Cleanest way to measure tau is to measure this.
So you have this, if I change the optical function of and what else do I expect to take this for different now?
Yes, you are for that. So this is E mode power spectrum for different value of tau. So after some time, like around 20, all are same. Most of the difference is in this. So if it is 0.04, you get something like this. If it is 0.08, it is something like this.
For high angular scale,
High.
because when the tau is increasing, the medium is becoming optically dense, thick. So the CMB photon can
Now the amplitude goes as t to the power minus 2 tau. So if you have more tau is more. I think the peak is here. You see a peak.
explain this.
How is measured at some high action?
So we measure integrated tau. We don't know from where it is. So that's how it's integrated. The this tau we can write it from our position. We integrate this quantity, function scattering, number density of electron, and the scale factor, and this is the conformal time dn. So it increases. So the I XC parameter, which is the free number density of the electron. Free number density. Previously it was 1, then it suddenly decreases. So then everything decoupled, like the photons decoupled. This tau is basically capturing when it becomes ionized because of the heating of the medium. So this is HC versus Z. Okay. So light density becomes like 1, then it becomes 0, then it increases. So this is what is basically tau. So tau is this integrated quantity which has a signature on this power.
Is that
Electron density, X, which is electron density over number of hydrogen atoms, number density of the. This is like a dimensionless quantity. Both cases as AQ. No, this is the so we get integrated quantity. This quantity. Okay. So it's up to you. We don't know. So basically, if you say the first stars are formed, so say it's up to 50, you can integrate from 0 to infinity, 0 to 50. You can integrate up to 1100, but then you know nothing there. Skip some part. Okay. So basically, this is the actual object. So they try to measure each L, what is the power, and try to fit those models and see what is the value of tau. So you can see it's very difficult to like consistent with 0. You take the error box, but all the points are above, so it means that it's not 0. It's not negative positive. So basically, from this peak, you can tell what is the value of tau. That is one, I think 2015 paper. So they put a limit on tau, which is 0.06. So from WMAP, it was very high. So people thought that it happened much earlier. Now with more and more data, it becomes closer to 0.05 or 0.06. And from Gunn-Peterson effect, we know that it should be higher than 0.045. So it is like a sheet of 6. So it means that it happened something around the organization completed at redshift of 8.
So if reionization happens earlier, then we expect more number density of electron. We expect more
Value of tau.
but we are not expecting.
So this is the value before. The WMAP is like 0.1. Then it keeps on decreasing with WMAP 3, WMAP 5. With Planck, it was close to WMAP 9, but with large error bar. It is around 0.08, and now it decreases to 0.05. So this is one of the key parameters which people try to understand, like the evolution of tau. And this is the hard, like from the astrophysical constraint is that it should be greater than this. It should not be less than that. Okay. And we are almost hitting this. So at some point, if it goes below this, there is a serious problem. So cosmology tells you value of tau, which is much less than what you expect from Gunn-Peterson effect. So this was 2018. Now I think people are going a bit up. So it all depends on how well you understand the photons and you clean the photons. So we measure from 0 to 1100. So it's an integrated quantity. So from us to time, everything is there. So assuming the structures are formed, we are finished at that redshift of 8. Basically, you get value. If it happens earlier, you get larger value. So with WMAP, it is reionization happened at redshift of 8.
optical with the size the start of the animals or take them.
It's like 50. There is some definition like it's 50%. Like it's closer towards the end of the I think I will finish. So this tau, previously we remember it was like 0.09, now it is 0.06. So this we don't see in the data. It has implications for people who are interested in CMB or primordial gravitational wave data. So this tau, if it is less for r equal to 0.01, we should expect a lower amplitude of the power spectrum. So tau is always CMB people prefer, so that they can measure this signal. If it is getting lower and lower, then it is difficult, even for a particular same value of R. So this curve depends on the order of the parameter. R is the scalar to tensor to scalar ratio. So we have a scalar perturbation, vector perturbation, and tensor. Vector perturbation dies down with time. We have a scalar perturbation which gives you all the cosmology, and there is a tensor perturbation. So when you measure the temperature power spectrum, it has a contribution from both. The Ph.D. power spectrum, which is tensor is always less. It is hard to know how much is the tensor, how much is the scalar dominance. This primary B mode signal, only the tensor perturbation dominates. There is no scalar perturbation. If you can measure this, it can tell you what is the ratio of tensor to scalar ratio. So this is what people are interested in. So tensor perturbation only comes from gravitational waves. Gravitational waves, when the inflation problem is that we don't know what is the level of this tensor perturbation. So it depends on the inflation. So all the simple models are ruled out, and with models which predict lower value of tensor perturbation, those are still limited. So now the upper limit is like 0.0. So it is like -2 level. Simple inflation model like M square, phi square model, they predict order of 0.1, 0.2, like that. By detected. Later on, they found that most of the detection is correct, but then they did for the foregrounds is less. So once they account for the foreground, so most of the signal is accounted by. Okay. So basically, earlier people tried to measure this the value of tau to the temperature, and there was a huge error bar, and the value was pointing towards the higher value of tau. But once the correlation data is included, E of the value goes lower, and now it's around like 0.05, 0.06, around that range. So basically, from the tau, you can tell what ratio will happen and what is the delta reaction. Like, is it instantaneous or it is happen for certain time. So those things you can constrain from just from. Distinguish between different ionization models, like the passive ionization. You can see some signature on the E mode power spectrum. So those things can be distinguished. So next week, if those who are staying, Divesh Jain is coming. So he works on this passive ionization. So he is making those forecasts for future generation CMB experiments. So this is just to not to go into details, but basically in CMB also you can constrain those, constrain the reionization, epoch of reionization models. 10 minutes over there. Okay. Question.
What is the x-axis?
X-axis is tau, value of tau, and P is the probability. It's like Monte Carlo sampling when you're doing, you get a mean value and a distribution. So this is basically the likelihood. So it takes around one value.
Different experiments are filling in different values.
So not different experiments. So one experiment, depending on which part you take. So this is like taking only the LFI data. So LFI has a different instrument. So Planck has two LFI, low frequency instrument and high frequency instrument. 30 to 70 gigahertz is low frequency instrument, and 100 to 53 is high frequency instrument. So maybe they are systematic, so they divide instrument into two. Only from low frequency instrument, they try to measure L less than 30, what is the constraint. So this is maybe from the low frequency instrument. Let's see the color. Suppose you take only the Planck TT power spectrum and include the lensing there, everything about the population data, then you get a peak around 0.08, which dominant form. Experiment is not for designed for correlation. They just detected the correlation. Planck has a better sensitivity, but we cannot measure accurately the everything. So there is a lot of data can be extracted from the correlation. Then this is like combining, making different combination of this. This is the best low E mode. So from the Planck, you can only choose the best channels, 100 and 140. Leave the dust. Measure like 50% of the sky, what is the value of tau. So we are making different combination just to increase the signatomics. Sometimes the systematics is such a way that if you combine HFI and LFI, all the signal goes up. Collecting data in 2012. It worked for 4 years. 9 to 13, sorry. And the data released was like final data was a set of papers, and the data was released in April. So the team stopped collecting data. It was decommissioned. It took 5 years just to get the population data. So it is very complicated, and I assume that was government update. So that time there was no prior experience. So in the first year they measured the population, there was no population paper. The third year the first population paper came, and they get a very high value of stuff. This very population is not great. People are not learning, and it's not very simple because it depends on all the coordinate systems.
Using the 1 meter we can get the lower limit for in redshift for reionization, and then in the optical depth for concentrating, we can if we have a given reionization machine, we can get the upper limit also, right? But to know the reionization model, so is there any distinguishing between reionization models using the tau values itself, or do we need that beforehand and then we can compute the upper limit?
It's a smaller error, you can start rolling out those. So currently the plot I have. So you can see all these models with the same value of tau. So it depends on the error bar. All of this gives, like in the power spectrum, this much difference. Your error bar is smaller than this, but this can start distributing between. That is basically next generation experiment is trying to get smaller error bars. These models are very close, but some other models we can rule out. So I'm just looking, if you have very small error bar, other model which is far away, you can rule out those.
or with this 5 years data which you produce?
So basically, some people are making the maps. So there is a time stream data. It's not that you see the map directly. There is a time stream data which same thing. You have to go from time stream to the map. Once you do that, then there are many people. So this like one unit who are expert in map. Then they give it to user and see what are the problems with that map. If you found obvious problem here, then they go back and change the map making. So it's an iterative process. It's not that it takes 5 years to make the map. Maybe they made like 25%. They agree that there is no problem here. So they give it to user and everyone is, if they don't find anything exotic in the data, so then the map making is okay. To give you an example, temperature power spectrum. So they ignore one systematic and you see a bomb at around 1500. That is what 1500. And people will try to prove theoretical is not. So they make theoretical models to explain that bomb around 1500. It's a very small bomb. It's derived from biannual. And the person who calculated cosmological parameters for plan, Ghosh from CMB. So he believed that he was also searching, but he was not able to get new physics from the data. So he always converged on the 6 parameters. So when other people are founding those, so then he suspects that it cannot be. And people make a model of that, like universe model which predict that 1500 bomb. Then he told this to the map making people that what features or whatever you're doing, if you note some systematics, can produce this. So they missed one effect which produces this. So once it is corrected, taken into account, because there are like 50 systematic effects you have to take into account. So unless it is like a learning experience, you don't know beforehand what to cut. So once they realize that okay, this effect is important, they just remove it, then features go. So all those model of universe goes up. Still current data, people trying to find new physics, like beyond standard number, 6 parameters, more parameters. So he is trying to imply we throw away many, like maybe 10% of data weekly, 90% of data we throw away because of the cosmic rays. So suddenly the signal goes up and you have to throw away those data. But sometimes you see cosmic ray, you maybe throw away more data. So he restricted, he tried to get more data from the original time stream data. And the more data he introduced, it goes actually to the lambda signal. So it's basically like 10% extra data to the current whatever we have from plan, and is pointing towards lambda signal. So there is always some systematic or something left. So data analysis is not very simple, but people like to find some new feature in the data. So they can pick their favorite model into that. So it's like an iterative process, it's not very straightforward. Okay. So this is the last talk. So basically, we'll start again on Monday. So 9:30.